Begin our chapter on integration. So specifically what we are going to do is go through in detail the construction of the integral due to the French mathematician Darboux, which it turns out is actually equivalent to the construction of the integral by Riemann, right? So the integral that we develop can, be alternatively called the Darboux integral or the Riemann integral. It is simply that the construction procedure that we will adopt when we go through this chapter is going to be the one by Darboux, because that I think is easier to explain and understand, right? So let us begin with some definitions. Let f be a bounded function on, let's say, the interval AB. So throughout we will be doing integration over an interval of this form, where again it will be implicitly assumed that A is less than B, right? So for S, which is a subset of the interval AB, define the following objects. Capital M F comma S is going to be defined as the supremum of the function values taken over S. Similarly, small m f of S will be defined to be the infimum of the function values over the subset S. Okay, so these are two objects that we will use in the construction of the integral. We need another definition of what is called a partition of the interval AB. So a partition, say P of AB, is basically an ordered collection of points. It's a finite ordered collection of points. Is a finite ordered set of the form T0, which is A, which is less than T1, which is less than T2, all the way up to something being less than Tn, which is the same as P, right? So a partition of the interval will graphically break up the interval into n subintervals, right? So if this is A, this is B, well, A is the same as T0, maybe T1 is here, T2 is here, and so on, and then finally Tn is equal to B, right? So these n+1 points, T0 through Tn, where T0 is the lower endpoint of the overall interval under consideration A, Tn is the upper endpoint, and these remaining points T1 through Tn minus 1 are strictly ordered. They will basically chop up the interval AB into n subintervals, right? So such a chop, if you will, is called a partition, right? So now, based on the definition of capital M, small m, and a partition, we can define what are called the upper and lower Darboux sums. UFP, the upper, this UFP is called the upper Darboux sum. Right, and it's going to be defined as summation from 1 through n of tk minus tk minus 1. This is the width of the kth subinterval times the supremum of the function values taken over the kth subinterval, f comma tk minus 1 to tk. Alright, analogously, the lower Darboux sum for the function f over partition P is going to be the similar summation, except that I multiply the width of the interval by the infimum of the function value taken over the interval. So tk minus 1 times m of f comma tk minus 1 to tk. Right, so this is called the lower Darboux sum. Right, so pictorially this should match some intuition that you might have about the integral. So if I am to say visualize the upper Darboux sum, suppose I'm looking at say a function like this, where let's say this is a, this is b. So you first have to define the upper and lower Darboux sum. You need to define a partition. So the partition is basically maybe a bunch of points like this. These don't have to be equally spaced, mind you, right? So now what you do is you break up the interval AB into the subintervals that are specified by the partition. And in each of these, you basically multiply the width of the subinterval with the supremum of the function value over that subinterval. Now, since I have drawn what looks like a continuous curve, the supremum over a subinterval is the same as the maximum over the subinterval, right? So the upper Darboux sum in this case would basically be the sum of the areas of these rectangles. Right, so this area would essentially be UFP. Right, an analogous picture can also be drawn for LFP, where in each subinterval, the height of the rectangle, so to speak, will actually in this case be the minimum of the function values over the subinterval rather than the maximum. Okay, so that I hope gives you a clean visual of the upper and the lower Darboux sum. Right, another immediate takeaway is that these guys are in fact well cleanly bounded. Right, so maybe I'll just squeeze that in here. So note is that if you look at m of f comma ab times b minus a, this is in fact a lower bound on the lower Darboux sum. The lower Darboux sum is of course always less than or equal to the upper Darboux sum, which in turn is upper bounded by m of f comma b minus a times b minus a. Right? So what this means is that the upper so clearly the upper Darboux sum is greater than the lower Darboux sum. That just comes from the fact that in one case you take the supremum of the function values, in the other case you define an infimum. So for any partition, UFP is greater than or equal to LFP, and further UFP can be upper bounded by, this is an easy exercise for you to see, that it is upper bounded by the width of the overall interval b minus a times the supremum of the function value across the board. Right, and I should have said a comma b here, sorry. So the second argument here is a comma b. Yeah, and similarly the lower Darboux sum is further lower bounded by the width of the overall interval b minus a times the infimum of the function values across the board, right, over the entire interval from a to b. Okay, so with this basic background, we are now in a position to define the integral itself. So recall that the upper Darboux sum is actually defined for a particular partition, right? So now what we are going to do is define UF to be the infimum of all upper Darboux sums over all partitions, right? P is a partition of AB, right? So this U is called the upper Darboux integral. I'll write that in a bit. And similarly, you take all of the possible lower Darboux sums LFP and consider the supremum of those over all partitions, L of FP, such that P is a partition. right? So as I said, this u of f is in fact called the upper Darboux integral. Right, this infimum is always going to be cleanly defined because of the fact that we have assumed that our function f is bounded, and remember we gave a lower bound, right? U of f and L of f, U of fp and L of fp are in fact bounded objects, so which means that these infs and soups are going to be real numbers given that the function under consideration is bounded, right? Similarly, this LF is called the lower Darboux integral. Okay. Now, one fact that we will prove, I think later in this video, is the following. So we will show, even though for a particular partition we know that UFP is greater than or equal to LFP, what we will show in fact is that the infimum of UFP, which is what UF is still going to be greater than or equal to the supremum of all possible lower Darboux sums. This is true for any function. Okay, the infimum of the upper Darboux sums is in fact going to be greater than or equal to the supremum of the lower Darboux sums. All right, and then finally we will say that a function is integrable if the upper and the lower Darboux integrals agree. So if u of f is equal to L of f, we say f is integrable. All right, integrable I guess over AB. And we will denote the integral as follows: a to b f of x dx. Now, why this dx business comes in and why is the integral written in this manner, right? That is something that hopefully, time permitting, we will get into. But at this point, just think of this as the notation for the integral of the function f from a to b, right? This integral will just be defined to be u of f is equal to L of f. Okay, so this is in fact the definition of the Darboux integral, which, as I mentioned before, is in fact equivalent to the definition of the Riemann integral. What do I mean by saying that they are equivalent? The definition of the Riemann integral itself, the original definition, is slightly different, but one can show that whenever a function is Riemann integrable, it is also Darboux integrable, and the integrals agree. Similarly, whenever a function is Darboux integrable, it is also Riemann integrable and the values of the integral agree. So therefore, I can think of this equivalently as a definition of the Riemann integral as well. Right? So at this point, we'll stop saying Riemann or Darboux integrable, we'll just say integrable. Okay? So this is the definition of the integral. So that is, I look at all possible upper Darboux sums, take the infimum of those, take all possible lower Darboux sums. When I say all possible, this is across all possible partitions. These partitions, this includes the, arbitrarily fine partitions of the interval, right? Take the supremum of all lower Darboux sums, and if these two numbers agree, then we say that the function is integrable, and that value of the upper / lower Darboux integral is in fact what we will call the value of the integral of the function. Okay. So before we build any further on the definition itself, what we will do is go through a couple of examples. Yeah, and before I go through the examples, I just want to highlight that the property that u of f is greater than or equal to L of f for any f, irrespective of whether f is integrable or not, is something we haven't proved yet. This is something we will prove. But at the moment, trust me, while we go through these examples, that inequality is in fact true. Okay, so the first example we are going to consider is f of x is equal to x square, and we want to try and integrate this over the interval, let's say 0, b, where b is naturally positive. Okay, so we know therefore, because this is a monotone increasing function, we know that UFP and it's continuous, of course, right? So it's just going to be summation of, let's say, tk minus 1 times tk square, right? Because the maximum of the function is going to be attained at the right endpoint of the subinterval, right? So 1 through n, and similarly LFP is going to be summation from 1 through n tk minus 1 the whole square times tk minus 1 the whole square, right? So the lower Darboux sum will be dictated by the function values at the left endpoint of each subinterval. Okay, now let me further consider a uniformly spaced partition, right? So let's take tk to be k times b by n, right? So this corresponds to a uniform partition. Okay, under this uniform partition, it turns out that I can actually write out an expression for the upper and the lower Darboux sums, right? That's the reason we are taking, for this particular example, a uniform partition. So u of fp will in fact be summation, let's say k running from 1 through n of, well, the width of the interval, which is going to be equal to kb by n. No, sorry, this is going to be tk, right? That tk square into the width of the interval, which is going to be b by n. Alright, so you can now simplify this to b cube by n cube times summation k square running from 1 through n. Now this again has a simplification, b cube by n cube times n into n plus 1 times 2n plus 1 by 6. Okay, that's the expression for summation k square running from 1 through n. Now, this is what the upper Darboux sum looks like for a uniform partition with n subintervals. Now I can ask myself what happens to this as the number of subintervals goes off to infinity, right? So you can see that as n goes to infinity, this will in fact converge to b cube by 3. Okay, so therefore I can conclude from this calculation that u of f, which is the infimum overall partitions, is going to be at most b cube by 3, right? Because uf is less than or equal to ufp for this particular choice of p, and so now if I take the limit as n gets to infinity, I can show that in fact the upper Darboux sum, so the upper Darboux integral, is at most b cube by 3. Right? So similarly, I can do something for the lower Darboux integral as well. So specifically for this partition LFP, all that changes is that in fact your summation k square gets replaced by summation k minus 1 the whole square. Right? So again, I leave the details for you to verify, but this just ends up becoming summation k minus 1 the whole square, also running from 1 through n. So effectively summation k square from 1 through n minus 1. Okay, I leave it for you. Just plug in the same formula above and check for yourself that as n goes to infinity, this also in fact converges to the same value, b cube by 3. Right? So therefore my second conclusion is that LF, the lower Darboux integral, which is the supremum, remember, of all lower Darboux sums, is in fact going to be greater than or equal to b cube by 3. Okay, so now if I combine these two observations, that u of f is less than equal to b cube by 3, L of f is greater than or equal to b cube by 3, and the fact that u of f is greater than or equal to L of f, one concludes that in fact the value of u of f and L of f must both be b cube by 3. So since u of f is greater than or equal to L of f, we conclude that u of f must be equal to L of f must be equal to b cubed by 3, right? And so therefore the value of the integral in this case is b cubed by 3. Okay, this is the end conclusion is something that we all know ahead of time. What we have done is applied the shall we say the definition to prove formally that in this case the integral from a to b of the function x square is in fact b cubed by 3. Okay, now note that in this example I have already used the fact that u of f is greater than or equal to L of f. This is something that hasn't been proved yet and will be proved shortly. Alright, but given this, I mean, if you believe this property for now, then we have just demonstrated one example of the calculation of the integral. Alright, one more example to illustrate a function which is in fact not integrable. So let's see. Example. So consider the function f from 0, 1 to r such that f of x is going to be 1 at all the rationals and 0 for all the irrationals. Okay, now let us see if this function is in fact integrable. It is not, because of the fact that for any partition, you give me any partition, that's basically, so break up the interval from 0 to 1 into any collection of subintervals, and you will always find that UFP is equal to 1, because in each and every one of those subintervals there is at least one rational, and so therefore the supremum would be 1, and so UFP would be 1. Okay, similarly for every partition P, LFP is 0. Why? Because in every subinterval there is at least one irrational, right? And this is true for all partitions P. So what we therefore conclude is that the upper integral, which is the infimum of UFP over all partition, this must be 1. Similarly, the lower integral, which is the supremum of all of the lower sums across partitions, is equal to 0. Which implies that the function is not integrable. Okay, so that's the example. So now what we are going to do is, maybe for the next, our immediate objective in the remainder of this is now going to be to prove formally that u of f is always greater than or equal to L of f. So next what we are going to do is we prove that u of f is always greater than or equal to L of f. Right? In other words, for any function, the upper Darboux integral is always greater than or equal to the lower Darboux integral, and so integrable functions are those where in fact this inequality is replaced by an equality. Okay, but we will need a sequence of lemmas to arrive at this statement. So we will begin with the following result. Okay, so first lemma, if f is bounded on AB and P and Q are partitions of AB, with P being in fact a subset of Q. Okay, now what does it mean to say that the partition P is a subset of the partition Q? That means that the points that define the partition P are a subset of the points that define the partition Q, which in turn implies that the subintervals that are induced by the partition P are being further broken down, if you will, to construct the subintervals that define the partition Q. Right? So some of one or more of the subintervals in P are going to be further chunked up to form the subintervals of partition Q. So we will say that Q is a finer partition than P. So Q is a finer partition than P. Okay, so if all of this is true, then what can I say? The claim is that L of Fp is less than or equal to L of Fq, which in turn is less than or equal to U of Fq, which is less than or equal to U of Fp. Okay, so what we learn is actually, so that's the statement of the lemma. So what we are learning is actually something that is quite instructive, in that it tells you how these upper and lower sums behave as your partitions become finer, right? What this is, so basically the middle inequality here is trivial, right? For a given partition Q, L of Fq is less than or equal to U of Q. So this bit is trivial. So essentially what remains is to show, let's call this B and let's call this A. What remains to show is that L of Fp is less than or equal to L of Fq. What is the interpretation of this? The interpretation is that as you make your partition finer, the lower sums become greater. And what the inequality A tells you is that as you make your partitions finer, the upper sums will actually decrease. Right? So as you make your partitions finer and finer, the lower sums keep increasing, the upper sums keep decreasing, and integrability occurs when in fact the supremum of the lower sums will in fact match the infimum of the upper sums, right? But we haven't gotten there yet. The key point of the inequalities A and B are that they move the upper and the lower sums in opposite directions, right? So when you make a partition finer, the lower sum increases, the upper sum decreases. Right? These are our two takeaways from this lemma, if you will. So the middle inequality, as I said, is trivial. Right, so we prove B. Proof of A is going to be similar. Okay, so how do we go about proving this? Now, what we know is that Q is a finer partition than P, right? So by induction, it suffices to check the inequality if Q has just one single point more than P, right? Because by applying this induction, if one can, then the inequality will only continue to hold if you add more and more points to the partition. So by induction, it suffices to check the inequality B when Q has a single point more than P. Right? In other words, we are going to take P to be, let's say, T0, which is A, less than T1, less than T2, all the way up to Tn, which is equal to P. And I'm going to take Q to be as follows. It's going to be T0 less than T1 less than all the way up to Tk minus 1, which is less than U, which is less than Tk, right, which in turn is further less than Tn. Okay, so I have added in the partition Q exactly one extra point U, which lies between Tk minus 1 and Tk in the original partition. Okay, so this is how we are going to set up the notation for P and Q. Now what I want to do is look at the difference between LFQ and LFP. Right? Now note that in all, if you look at, well, in all areas except for the region between K minus 1 and Tk minus 1 and Tk, the subintervals in P and Q are in fact identical, so which means all of the terms corresponding to those would in fact just cancel out. Right? So what are the differences? Well, in Q you would have two terms which correspond to the two subintervals, right? There's one from Tk minus 1 to U and one from U to Tk minus 1. So Tk minus U times in fact the infimum of the function over this interval from u to tk plus u minus tk minus 1 times m of f over tk minus 1 comma u, right, minus tk minus 1, this is the corresponding term from p, right, times m of f comma tk minus 1 comma tk. This is what the difference is going to look like, right? But note that the infimum here is in fact over a larger over a superset interval as compared to the infimum here and here. In other words, the first of these infimums, that is the infimum over the overall subinterval tk minus 1 to tk, is only going to be further smaller than each of the remaining two, right? And that itself is all it needs for me to conclude that this difference is in fact going to be greater than or equal to 0, right? So, but m of f comma tk minus 1 to tk is in fact going to be less than or equal to m of f over tk minus 1, and it's also going to be less than or equal to m of f over tk minus 1 comma u, right? So because the infimum over the overall subinterval from tk minus 1 to tk is going to be less than or equal to the infimum over each of the subchunks of that subinterval, it now follows that this difference is in fact greater than or equal to 0. L of fq minus L of fp is greater than or equal to 0. Okay, so it's actually fairly straightforward to argue that indeed, as you make your partition finer, your lower sums will in fact increase, right? Because you are taking infimum over finer and finer intervals as opposed to taking infimums over coarser intervals. So the infimum over the coarser and larger subintervals will in fact be smaller. Okay, so that completes the statement of this lemma. Now we move on to the next, which is going to be an application of this. So now that we know what happens to upper and lower sums as you make your partition finer, we will now be able to prove the following even stronger result. So once again, let f be a bounded function. Right, and let's say P and Q are any partitions of the interval AB, then in fact L of Fp is in fact less than or equal to U of F comma Q. Okay, now I'm not imposing anymore the condition that P and Q are related in any manner, that Q is finer than P or anything of that sort. You give me any two partitions. What this lemma now tells you is that the lower sum is always going to be upper bounded by the upper sum across any arbitrary partitions. Okay, so how do we go about proving this? What we are going to do is consider the partition which is obtained by the union, partition. Partition P union Q. Okay, on this, well, it turns out that L of Fp, remember P union Q is a finer partition than P. So therefore the lower sum is only going to get larger. Now L over this union is of course going to be less than or equal to U over this union, and since the union is a finer partition than Q, well, this is going to be further upper bounded by UFQ, right? Because going here for this inequality, what matters is that when you make the partition finer, the upper sum decreases. For this inequality, you use the fact that as you make the partition finer, the lower sum increases, right? Patch these two together and you're done, right? So therefore, for any partition P and for any partition Q, the lower sum over P is going to be less than or equal to the upper sum over Q, right? And this in turn essentially implies the claim I had made before, that the lower Darboux integral is less than or equal to the upper Darboux integral, right? So let F be bounded over, let's say, AB, then L of F is less than or equal to U of F. Okay, so the proof is now going to be a trivial consequence of the lemma that we've written just above, that for any PQ, L of FP is less than or equal to U of FQ, right? So all I'm going to do is take the infimum over Q and the supremum over P, right? So I could do this sequentially. L of Fp is therefore less than or equal to the inf of U of Fq over partitions Q. Sorry, right? This is in fact the same as U of F, right? So therefore I know that L of Fp is less than or equal to U of F, right? Now I can take the supremum over P, so therefore supremum of L of Fp over partitions P is less than or equal to U of F, right? But the supremum is in fact the same as L of F, right? And that completes the argument, right? So to recap, what we have shown is that under our construction, the lower, for any bounded function over any interval, the lower Darboux integral is always upper bounded by the upper Darboux integral, which kind of justifies their names as well. And a function is integrable if these two in fact agree. In other words, the L of F and U of F values in fact agree. Okay, so we will conclude this by basically providing a Cauchy criteria for integrability, right? This is going to provide a sufficient condition, actually a necessary and sufficient condition for the integrability of a function. So Cauchy criteria for integrability. Okay, so theorem: a bounded function f on AB is integrable if and only if for any epsilon greater than 0 there exists a partition P of AB such that the gap between the upper sum and the lower sum is in fact less than epsilon. Okay, so what we are saying now is that a function is integrable if and only if, no matter what positive epsilon you choose, I can come up with a partition such that the gap between the upper sum at P and the lower sum at P is in fact less than epsilon. Okay, so this gives us a necessary and sufficient condition for the integrability of the function f. Okay, so the proof you should expect is of two parts. So part 1, so say f is integrable. right? So which means that there exists, that is u of f is equal to L of f, right? Now therefore there exist partitions P1 and P2 such that the following conditions are true: that u of f comma P1 is in fact going to be less than u of f plus epsilon by 2, right? Why is this? This follows from the fact that u of f is the infimum, right? So the fact that u of f is the infimum means that it is in fact the greatest lower bound, right? So if you give me anything more than u of f, like u of f plus epsilon by 2, this is no longer a lower bound on u of fp. So I can always find a partition p1 such that it is less than epsilon by 2 more than the infimum, right? Similarly, I can find a partition p2 such that L of f comma p2 is in fact greater than L of f minus epsilon by 2, okay? Which means that if you now look at u of f comma p1 union p2, right, this is going to also in fact be less than, because when you make the partition finer, the upper sum further decreases, right? So u of f, sorry about that, u of f minus epsilon by 2. And similarly, if you take u of L of f comma p1 union p2, this is also greater than L of f minus epsilon by 2. Now all you have to do is patch these two together. So since u of f is equal to L of f, we have that u of f comma p1 union p2 minus L of f comma p1 union p2 is in fact less than epsilon, right? And that is essentially what we needed to prove the first part, right? So what the proof is actually fairly trivial if you think about it. All we are saying is that you can find a partition which is within, such that the upper sum is within epsilon by 2 of u of f. You can find another partition where the lower sum is within epsilon by 2 of L of f. Since u of f and L of f are equal, well, the gap between these two is at most epsilon, but these are not necessarily the same partition, right? But you can further shrink the gap by considering the partition which is obtained by taking the union of these two. That's kind of the argument, right? And so this is how you show one side of this statement. The other side would be to assume that this condition is true and then show that u of f is equal to L of f. So suppose for any epsilon greater than 0, there exists a partition P such that u of f comma p minus L of f comma p is in fact less than epsilon. Okay, now this in fact implies that, remember, u of f is in fact the infimum of u of fp. So which means if I take u of f minus L of fp, that in fact will further shrink this value down. Further, L of f is the supremum, right? So from the previous conclusion here, it follows that the difference between u of f and L of f is also in fact less than epsilon, right? Because for a given partition, if the gap between the upper and the lower sum is less than epsilon, since u is further small, since u of f is further smaller than u of fp and L of f is further larger than L of fp, the gap between u of f and L of f has in fact had to be less than epsilon as well, right? But since this is true for any positive epsilon, it follows that u of f is equal to L of f. Since this is true for any epsilon greater than 0, and remember that u of f is already proved to be greater than or equal to L of f, it follows that u of f must be equal to L of f, right? And that completes the argument, right? So in conclusion, what we have proved is the so-called Cauchy criteria for integrability, which is to say that a function is integrable if and only if, no matter what epsilon you pick, I can find a sufficiently fine partition of the interval a to b such that the gap between the upper and the lower sums on that partition will in fact be less than epsilon. So if you can do this for every positive epsilon, the function is integrable, and vice versa. Alright, so we will stop here, and in the next video what we will do is look at several types of functions which in fact can be shown to be integrable given the definition of integrability.